What if the biggest gains in AI aren't just about bigger models, but about better training, better routing, and better simulation? In this episode, we dive into three fascinating papers. One that distills diffusion models into faster, higher fidelity generators. One that exposes how far simulated users still are from real human behavior. And one that reveals when mixture of experts models route tokens to the wrong specialists. Together, they paint a vivid picture of AI's next frontier. Let's explore the first paper, Continuous Time Distribution, Matching for Few-Step Diffusion Distillation. Continuous Time Distribution, Matching for Few-Step Diffusion Distillation, introduces CDM, a distillation framework that removes the discrete time-step constraint of DMD2 and trains directly in continuous time. Instead of anchoring supervision to a fixed inference grid, CDM samples a random backward simulation length N1U, 1, Nmax, and uniformly draws continuous anchors. TI belongs to 0, 1, which empirically improves visual fidelity and HBSV3 versus strict schedule alignment. The core novelty is the CDM loss. It performs velocity-driven Euler extrapolation to off-trajectory latents xt equals xt plus t, v theta xt t c, then matches distributions at these drifted points, explicitly regularizing the student's material derivative, dv theta, d tau, and reducing truncation error in few-step sampling. The method also reinterprets the DMD losses. The CFG augmentation term aligns text-image conditioning through an implicit classifier gradient, while the distribution matching term matches the student to the teacher's CFG-free distribution, not merely as a stabilizer. On SD3, medium, and long cat image at 4 NFE, CDM reports state-of-the-art results, including HP SV3 9.561 on SD3, medium versus 9.176 for DMD, and 10.65 on long cat image versus 9.629 for DMD, while matching or exceeding the 100 step teacher on several metrics. The training cost rises to about 1.8 times DMD, but inference latency stays unchanged at 246 ms, image because the distillation adds no runtime overhead. Let's explore the second paper, Measuring and Mitigating the Distributional Gap Between Real and Simulated User Behaviors. This paper argues that matching the surface style of real users is not enough. User simulators must match the full distribution of behavioral modes. The authors propose a three-stage metric that first uses an LLM, specifically Quen 3, 5, 1, 2, 2b, A1, 0b, FP8, to summarize each conversation along 6 facets: requests, responses, context, communication style, damsel dialogue acts, and SGD dialogue acts, then embeds those summaries with Quen 3. Embedding 8b clusters them with k-means at k equals 500 and measures divergence with forward KL, backward KL, and Jensen-Shannon, validated by an odd one-out study where annotators identified cluster intrusions 86.7% of the time. The method exposes a large real versus simulated gap across 24 simulators evaluated on 5,000 WildChat conversations, each for coding and writing. The best systems, GPT-5, 4, and Gemini 3.1 Pro, still diverge substantially from real users, with Coding.js around 0.246 and 0.248, and Writing.js around 0.466 and 0.479, while open models are generally worse. User LM 8b is notable for strong trained simulator performance, but is confounded by training overlap with WildChat. The paper's key novelty is that the gap is not uniform. Simulators are relatively better on requests and context, but much weaker on communication style and dialogue acts, where fine-tuned simulators outperform general-purpose LLMs. A TF-IDF analysis of behavior clusters shows simulators often capture iterative troubleshooting, but miss terse, transactional exchanges and hallucinate excessive politeness. Finally, the authors show that mixing behaviorally complementary simulators, such as Gemini 3.1 Pro with GPT-5 and 4, reduces JS divergence below either model alone, suggesting simulator routing as a practical path toward closing the sim-to-real gap. Let's explore the third paper, When Are Experts Misrouted? Counterfactual Routing Analysis in Mixture of Experts Language Models. This paper asks whether the expert subsets chosen by standard top-K routers in mixture of experts language models are actually the best equal compute choices for each token, rather than merely the ones the model happened to execute. The authors test 4 open-weight MOE models: Quinn 330B, A3B, GPT, OSS 20B, DeepSeek, V2, Lite, and OLMO 1B, 7B, by freezing the model and comparing the router's selected route against 32 Gumbo Top K alternative routes from the same 3-2 expert candidate pool, scoring each route by the realized next token probability on verified reasoning trajectories from Math Level 5, AIM 2024, Plus 2025, HMMT 2025, and GPQA Diamond. The key result is strongly token conditional. On confident tokens, the standard route is near optimal, but on fragile tokens, it becomes almost uninformative. For Quinn 330B A3B at the final Mo layer, the standard route is best on only 0.8% of fragile tokens, while the best sampled equal compute route improves next token probability by 20.4 percentage points. Similar fragile token gaps appear on AMI and HMMT at about 19 points, on GPT OSS 20B at 11.8 points, on DeepSeek V2 Lite at 24.9 points, and on OLMOE 1B 7B at 20.8 points. The paper argues this is a counterfactual blind spot in ordinary MOE training because the cross-entropy loss only evaluates the executed route, and load balancing losses depend on aggregate routing statistics, not token-level counterfactual route quality. To probe causality, the authors introduce expert preference optimization, a router-only update that changes fewer than 0.001% of parameters by retraining only the final layer router. This shifts pass at K upward on AIM and HMMT for both Quinn 330B, A3B, and GPT, OSS 20B, supporting the claim that some failures come from misrouting rather than expert capacity. That's a wrap on today's AI paper highlights. Thanks for watching.